This is a conservation of energy problem involving a rolling disk. It's similar to one that's in the lecture notes. And the chapter notes we have a disk, not a sphere, that rolls up a hill. Let's look carefully at how one answers the question, at what speed does the rolling sphere arrive at this higher elevation? So we have a sphere whose center of mass translational velocity is v naught. And if you recall the relationship shown here, the angular velocity of our sphere is omega naught, which can be written in terms of v as v naught over r. We'll do that later. Assuming there's no significant air resistance or friction, the total energy earlier equals the total energy later. The total energy will consist of three parts. Two kinds of kinetic energy: translational kinetic energy, 1/2 mv squared, and rotational kinetic energy, 1/2 I omega squared. And then the third kind of energy, gravitational potential energy. Three energies on the left side of the energy conservation equation, three on the right. Let's start on the left. One half m v naught squared plus 1/2 of 2/5 mr squared times omega naught squared. But omega naught is v naught over r. That's your omega, it gets squared. The reference level for gravitational potential energy is taken to be that line there. And so the initial elevation h is 0. And so the gravitational potential energy initially is 0. Let's do the right side. It's 1/2 mv squared plus 1/2 of I, which is 2/5 mr squared times omega unsubscripted squared. But omega, according to that expression, is v divided by r. It gets squared. Now let's simplify many of these terms. Let's go to the left side. That 2 cancels that one. And that r in the denominator gets squared. It cancels the squared r up there. Right-hand side, that 2 cancels that one. And that r in the denominator, which gets squared, cancels the r upstairs. It's squared. Back to the left side. We have an mv naught squared and an mv naught squared. This multiple of mv naught squared can be written as 5/10 v naught squared. And 1/5 can be written as 2/10 v naught squared. And that equals the same sort of situation here. 1/2 is 5/10 v squared plus 2/10 v squared for a total of 7/10 v squared. But let me not write down that until I correct a problem here. I failed on the right-hand side to take into account the gravitational potential energy, which is mg capital H. All right, the right-hand side then again is 5/10 plus 2/10 times v squared and an mgh. These two combine to give 7/10 v squared, and those two combine to give, no. These two combine to give 7/10 v naught squared, and over here we've got 7/10 v squared plus mgh. If I multiply both sides of this equation by 10/7, we have v naught squared equals v squared plus 10/7 gh. From this, we obtain the expression we're looking for the speed at the plateau. We have that v equals parentheses v naught squared minus 10/7 gh raised to the 1/2 power. Final result.